Good morning, everyone. Can you hear us? Okay, this is Walid Baraki. I'm the president and founder of Medicals International. So happy to have so many of you. We're about 750 attendees so far at this very nice seminar, presentation that Dr. Porros will be giving in a few minutes. Please join me from the comfort of your homes to welcome this grand speaker and good friend, Porros, who is a scientist, a thinker, an adventurer who undertook the challenge of making the placement of a contact lens on a deformed eye easy, accessible, a pret-a-porter rather than a custom-made that took months to get and to design to the need of the eye. Porros, a visionary who utilized numerics way before it was a la mode, creating a mathematical algorithm out of which to design a lens that fits so many of our keratoconus patients. And trust us when we say it works, because at Medicals, we have fitted so far way above 150,000 of these lens designs, and it worked very well. So allow me now to give the stage to Porros, and Paul, you should start your video and start now, I think, the slides presentation.
Can you see that yet, Walid?
Yes, you should go ahead now.
Has that opened on your screen, Walid?
Yeah, the screen is excellent. You have the slides now, the first slide on, so you can join, and you can as well, have your picture on if you like.
Okay. No, I'll leave my picture off. It's fine.
Okay.
Thank you. Good evening, everybody from New Zealand. I understand we have somewhere near 1,300 people joining us this evening. So thanks to Medical International for putting this webinar together, and you have got certainly an incredible response. So what I want to do tonight is just cover the advanced options for rose-cage designs. And I'm firstly going to cover the corneal designs and then move on to the XL design at the end of the webinar. So for those that fit rose-K, you may be aware that you have many toric and ACT options available to you. They include toric periphery, ACT or reverse ACT, where in fact, rather than tuck it in, you tuck the edge of the lens out, and that's available in up to 2 quadrants. You can have a front toric. Quadrant-specific edge lift is also available in most of the corneal lens designs, but not used as much as it is in the XL design. You can have a fallback surface toric, or you can have any combinations of the above. And all in all, rose-K offers about 150 different designs within its family of lenses. I don't want to go into any detail about the 5-step fitting system, except to say, for those that don't know my designs, it's very well documented on videos on the net, and you can look it up there. But I will just mention 3 aspects of the fitting, just to refresh our minds about what we're looking for. So with the 5-step fitting system, you always start with the central fit, you move to the peripheral fit, the diameter, the location, and finally the lens movement. And once you become familiar with the designs, you should expect to get in excess of an 83 first fit success rate with your first ordered lens. So what are we trying to achieve with a corneal lens is the image on the right-hand side here. So this image shows very light feather touch at the apex of the cone. The central image here shows a slightly excessive touch, and the left image shows excessive clearing of the cone. So you're going to change the base curve up and down to produce the pattern you see on the right-hand side. Remember, the highest point on the cornea with the post-graft design is not necessarily central. It may be along the post-graft interface. When we move to the peripheral fit, the second step, what we're trying to achieve is a fluorescent band at the edge of the lens, 0.6 to 0.8 millimeters wide. It may be different on the nasal side to the temporal side. The reason why is the nasal cornea is often flatter than the temporal cornea. If that's the case, you just average the two, but we're looking somewhere between 0.6 to 0.8 wide, and you're going to change your edge lift value until you achieve this pattern. Location is mainly controlled with corneal lenses by base curve, the edge lift choice, and also the diameter of the lens. If you look at the left video, you can see how this lens continuously rides down. If we change the parameters, we go flatter from 6.6 to 6.8, we go slightly larger, and we go from a standard lift to an increased lift, you can immediately see how the image on the right centers up much better. So by changing these parameters, you can alter the location of the lens. And finally, on the movement, we're trying to achieve a movement on the cornea with the lens of about 1 to 2 millimeters to achieve good tear exchange. In these videos, all I've done is tighten the edge lift, and you can see the second image here, the edge lift is not as wide as here. And then on the third one, we can see, sorry about that, I'll go back there. But on the third one here, so we'll just open up all of these now. You can see on the right, there's no edge lift, very little movement, very little attachment to the lid. So by changing the edge lift, you can change significantly the movement of the lens. So let's move on to looking at why we need asymmetric or toric options. The most common problem we have with the keratoconus is seeing this type of pattern where we have the cornea flattened in the horizontal meridian and steeper in the vertical meridian. This causes the lens to bear excessively heavily in the horizontal meridian because so often with keratoconus we have with baroblic astigmatism. That causes the lens to ride lower, to be more uncomfortable, to lift off inferiorly here at the bottom here, which often contacts the lid, often causes 3 and 9 o'clock staining because there is no clearance here at the edge of the lens, makes the lens less stable, and it all up reduces your wearing time. So the first thing you can do is consider the Rose K2 toric periphery. It can be used with all my designs. Very simple to use. It does not require any special trial set at all. And I have set the standard toricity for the toric periphery at having an 0.8 difference in the two meridians. You may say, why? Simply, I analyzed all the toric periphery fits I had done, and that was the average over about 100 fits. So I set the 0.8 difference as the standard toricity. However, any degree of toricity can be ordered in 0.1 steps from as low as 0.4 up to as high as 2.0. Once you get above 2.0, you probably need a full back surface toric. As the diameter increases, a toric periphery is more likely to be required, and I'll cover that a bit more. So you can see with a toric periphery, what we're going to do is steepen one part of the lens and flatten another. The central part of the lens here really doesn't change. So in this part of the lens, there's no change to that part of the lens at all. So the back optic area is unchanged. What we're going to change is what we see outside this white circle. So we can see here, we're going to steepen the lens here, and we're going to flatten the lens in the horizontal meridian. Also, the toricity can be split asymmetrically. For example, if you decided that you required more flattening in this meridian than you required steepening in this meridian, and in this one you might say, I'd like to flatten it more here than I'd like to steepen here. We're not seeing it too open here. So you might say, I'm going to have a 1.0 toricity, I'm going to flatten at 0.6 in the horizontal meridian, and I'm going to steepen at 0.4 in the vertical meridian. As I mentioned, you do not require any special trial set. You can fit from your standard Rose-K trial sets, and you can see the difference in the pattern here. This is on the same eye. This is with no peripheral toric, and this is just using the standard 0.8 peripheral toric. And you can see the difference in the fluorescent pattern. So this is going to be a much more comfortable lens, and it will in fact move and locate much better as well. In corneal lenses, to give you a rough idea, a difference in the sagittal height of the two meridians of anything greater than 30 microns, you should consider that you may require a toric periphery. So the first question here is, which of these two images will definitely require a toric periphery? I understand that you have the answer, you can answer on your computers. So Yara, you want to take over here, or that's all? And so the answer is the right-hand image will require a toric periphery. What is the reason why? If you look at the left image, you can see that we still have fluorescent at the edge of the lens in that flattest meridian here. So here we do not require a toric periphery. If we did, we may in fact lift the lens here excessively in that meridian, because the astigmatism is basically over the central cornea here and doesn't extend right out into the peripheral cornea. In the right-hand image, you can see how tight it is, both here and here. This was definitely causes problems and would cause the lens to ride lower and be much less comfortable. It was interesting on that particular to see that we had about a 50-50 polling, but we had more people right than wrong on that one. So just to go through the fitting of peripheral torics, you fit as per normal with the spherical Rose-K trial set, achieving a feather touch at the apex. You estimate the degree of toricity required or go with a standard toric periphery of 0.8. You can split the toricity equally or as required, and you can order a base curve 0.05 steep and adjust the power. You may say, why do you do that? Why don't we just go with the same base curve? Because I told you that nothing changes over the central cornea. The reason why is the lens is currently, look at this picture here, is bearing here and is bearing here. If we flatten the curves here and here, what effect will that have on the central fit? It will allow the lens to sit back closer to the cornea. So in corneal lenses, we have to allow for that. You have to think about that. The lab won't do it automatically for you. So if you're fitting a toric periphery, always fit it 0.05 steeper, and you'll need to make it a power adjustment. I'll cover that a bit later. Prism's really required, and the lens will have laser marks along the flattest axis, so it can tell you how the lens is locating. There is ways you can estimate the degree of toricity. So if you use your 5mm topography ring, if you have, I know Medmont will show the 5mm SimKs as well, so you can use those. And if we go to a topography here and look at this down, so if you look at the 5mm ring, here's the 5mm ring. You would put your cursor on here. It will give you a particular reading. You put your cursor here, it will give you another reading. And in the opposite meridian, you do the same. You put your cursor here and here. You look at the average. So you'll have the SimKs and the two meridians. You take them away, So here we have a reading of 52. Here we have an average of 46.5. You take them away, and that gives you an approximate idea of the amount of toricity you require. So I found the 5mm ring to give the best indication of the amount of toricity. So moving on to the ACT design. The ACT or asymmetric corneal technology is available for all Rose K2 designs. One quadrant, usually it's inferior, is steepened only, as you can see in the diagram here. It provides better comfort and stability, and in some cases you get improved vision because of the stability of the lens. So you can see the difference here between having no ACT and the lens is lifting off. We can see some small bubbles appearing in the tear meniscus at the edge of the lens. And on the right here, you can see how this has changed the picture here. So we don't have that same lift off. We have a very even pattern around the edge lift. So this lens is going to be more successful than the lens on the left. I have defined 3 standard grades available for ACT, although you can in fact choose anything between 0.4 and 1.5 to actually tuck the lens in, and you can do that in 0.1 steps. So if we look at the left, the grade 1, 0.7 would be required. That's the difference between the curves up here and how much we're going to tuck. These are going to be tucked in 0.7 steeper. Grade 2 is where we tuck these in by 1mm, and grade 3 we actually alter it by 1.3. So the standard default ACT is grade 2. This is the most common one. In this one here, you would probably get away with actually requiring an ACT. This is not excessive liftoff. We have no bubbles. So we defaulted, this is the most default. If you just say I want ACT, the laboratory will default to this particular grade. So this is an ideal case to include ACT. You can see here the lens is lifting off inferiorly here. You can see some small bubbles appearing. The lens is not particularly stable, it's moving down. So the couple of things I would do in this image is the first, I would steepen the base curve. You can see here that this is riding heavily on the cone, and that's causing it to lift off. So I would steepen the base curve a little bit, and I'd add ACT grade 2 at the bottom of the lens. This is a good picture to show where ACT is not located. I'm going to stop the video right there. So you can see that that laser line started up here, and on each blink it moved around the clock in an anti-clockwise direction as we blinked. So the ACT didn't locate at all. The reason why it didn't locate is in fact because we don't have enough ACT. The lens is fractionally flat than it should. I'd go another 0.1 steeper, but in the lower part here you can see how it's lifting off. This was grade 1. We should have had at least a grade 2 ACT with this case. One little tip here, you'll need higher grades of ACT for flatter base curves and lower grades of ACT for very steep base curves. That's just the way the design works. In steeper base curves, when you actually add ACT, it tends to change the sagittal height in the lower part of the lens to a greater degree than it does in flatter base curves. One little tip here, only use ACT when it's necessary. Some inferior lift is often acceptable if it's not causing problems such as instability and comfort. I've seen people add ACTs to NC designs, which is the smallest lens. It's often fitted less than 8.5mm, so it's a very small lens, and in many cases just not needed. So don't use ACT unless you really have to. So how do you choose between using a toric periphery or ACT? A toric periphery requires some corneal symmetry. So usually you're going to require the lens to be steepened in the vertical and flattened in the horizontal. With ACT, you don't require any symmetry. And remember, you can put two lots of A. You can put, for example, lift off here, you can tuck that in, and you can lift it off at the top. So you can have the choice of adding two ACTs to any lens. Next one I want to cover is front surface toric for the correction of residual astigmatism. Toricity is applied to the front surface of the lens only, and prism ballast extending over the optic zone is used to ensure correct orientation of the lens. The back surface of the lens remains unchanged. Inclusion of a front surface toric will not affect the central fit. However, in some cases, it can definitely affect the location and cause it to ride lower, which may close up the inferior edge a little bit. So again, my advice is don't use it unless it makes a significant improvement to the visual acuity. I have people send me images from all around the world where they've corrected a minus 050 cylinder on the front and the lens is riding very low. All I say to them is, look, take the sill out of the equation and immediately the lens rides up in a much better position, because the prism in many cases will cause the lens to ride a little lower. I want to now move to asymmetric options for Rose K2 XL. Very often with these larger lenses, you see very irregular pattern at the edge of the lens, like it's open here, it's closed here, it's closed here, it's a little open. So that's not uncommon to see with large lenses, because the conjunctiva is usually not a particularly uniform shape. So why toric periphery and ACT options are required in these large lenses? And we're just going to spend a little bit of time answering that question. As I said, the center of the lens here in toric peripheries is not changed. The sagittal height, if we had a very small lens, if the lens was made as small as that white circle, then the sagittal height between there and there would be very minimal, and therefore you won't need an ACT option. But as we move, or toric periphery option, but as we move out, the further we go out to the edge of the lens, as you can see here, the bigger the difference in the sagittal heights at 90 versus 0 here. So the bigger the lens goes, the more you have to think about using some asymmetric option. So for a corneal lens, as I mentioned, I set the toricity at 0.8 for my standard toric periphery. But when we start to make these bigger lenses, let's say this is around about a 10 millimeter lens. If we go then out to XL, so you're getting out towards 15 millimeters, you need another 50% of toricity to fit this, because this toricity will continue out from the cornea out over the sclera. So these larger lenses require a higher value of toricity to make them work well than a corneal lens requires. You have many options. You have a toric periphery with asymmetric split. You have ACTs and reverse ACTs. Reverse ACT is where you put the edge of the lens out instead of in. You have segment-specific ACT, which I will cover in a moment. You have quadrant-specific edge lifts, where you can change the edge lift in any specific quadrant. You have front torics, and you also have full-back surface torics. But full-back surface toric is used very, very rarely in these larger lenses. And again, you can have any toric, any combination of the above. You can combine a toric periphery with a front toric, or any of these combinations. The most common ones that we see used is toric periphery, the most common, ACT often used, quadrant-specific edge lifts, and toric, and the front toric. Those are the most common asymmetric options that I see being used around the world. So how do we choose between using quadrant-specific edge lifts, toric peripheries, or ACT? So here I'm just diagrammatically showing you how this works. So this is the edge of the lens, and this is the limbus, and this is the back optic zone of XL, which is somewhere between 8 and 9 millimeters, and it's aspheric. So if we look at quadrant-specific edge lifts first, when you change to or order a quadrant-specific edge lift, all you will change is anything outside the red circle. Nothing over the cornea will change at all. So all you will change is what really happens outside the limbus. And you can order up a different edge lift in each of these quadrants. What about toric periphery? A toric periphery, the curves actually extend right back to the edge of the back optic zone. So with a toric periphery, you're going to change the fit not only outside the limbus, but also on the peripheral cornea. So quadrant-specific edge lift only changes the fit outside the limbus. Toric periphery will also change the fit on the peripheral cornea in all those meridians. And ACT, although we talk about ACT as being a one quadrant, ACT actually changes the fit over 180 degrees, with the maximum tuck being in the center of the axis that you choose. So let's go into a little bit more detail with these particular options. So as I said, when you order quadrant-specific edge lifts, this will only affect the lift outside of the limbus. If we take an example here, you can see this lens is slightly tight here. We're not getting any fluorescence underneath the edge of the lens, which is causing this injection in this particular quadrant, nowhere else around. So we increase the edge lift in that particular quadrant. So the middle of that axis will be 225 degrees here. And immediately we open up the fluorescence and we alleviate the problem of the injection. For ordering, you state the axis of the center of the quadrant or quadrants that you want to actually have the quadrant-specific edge lift in. What about toric periphery? As I mentioned, you're going to here change the fit on the peripheral cornea as well as outside the limbus. So toric periphery is required in up to 40% of cases. Now that's extremely high, and around the world it's probably somewhere between 10 and 15%, so it's very underutilized. In fact, in some cases, there are some trial sets in semiscleral designs where they incorporate a toric periphery automatically into the trial set, particularly once you get up to 16 millimeters or more. The standard toric periphery is 1.2, and the toricity can be split asymmetrically in the two meridians. When you actually understand that modern technology has shown that less than 10% of scleras are actually spherical, you can see why we need to think about these asymmetric options with these larger lenses. So here's a picture of a toric periphery. This is a standard toric periphery and fitting quite nicely. You can see the bearing area just along inside the limbus here. So if we use the 1.2 standard toric periphery, you would steepen it by 0.6 in that meridian, and you would flatten it by 0.4 in that meridian. So unless you state that you want to split the two meridians asymmetrically, the lab will always split them equally. So they'll go the same amount steeper in one meridian and the same amount flatter in the other meridian. There's no need to state the axis, because these things, even if you put them in with the laser marks here, even if you put them in the not right position within a couple of blinks, they will actually rotate round and locate very well. They really lock onto the shape of the sclera very, very well. However, if you need to actually incorporate some astigmatism on the front, then the laboratory needs to understand the angle between the flattest back surface and the cylinder that you want on the front, so they know where to put it. So if you did need to incorporate residual astigmatism, you would need to state where the axis, or the flattest axis, is going to be. So the laser lines, when the lens comes back to you, it'll have laser lines along the flattest back axis to indicate exactly where it is actually centered. So here we have a toric periphery locating extremely well. You can add prism, but really it's just about never required, and I never suggest you do it initially. You can see how stable that lens is on the eye. Okay, here's your second question. What option should we use here for this particular fit? And I'm going to help you a little bit with some clues. So I'll just give you a moment just to watch this video as we move around the clock. So we're looking at here at inferiorly. Here we're looking at superiorly, and there centrally. So let's just take some snapshots of what's happening here. So at 180, we had excessive liftoff. At 0, we had excessive liftoff. At 90, the lens was tight, and at 270, the lens was tight. And also I'm just going to add the final image here, which is a good image of the overall fit of the lens. So we have some options we could use here. You could use a toric periphery. You might want to use ACT or reverse ACT. You could use a quadrant-specific edge lift, or you could use a toric periphery with a quadrant-specific edge lift. Darren, I'll just hand that over to you for the polling of this question. So we have the majority with the, I've answered toric periphery with a quadrant-specific edge lift. And that is actually the correct answer here. So why do we need a toric periphery with a quadrant-specific edge lift here? Let's analyze what's happening. Over the cornea, we have, with the rule of astigmatism, we have the lens flat or bearing excessively here and here, but in the vertical meridian we have exactly the, just looking on the cornea, but in the vertical meridian we have the lens open up vertically. So we have toricity. I'll just go back there, I don't want to move on to that slide yet. So here we can see the lens goes with the rule of astigmatism over the cornea. But what happens when we move outside of the limbus? It actually shows against the rule of astigmatism, with the lens being tight at 90 and 270 and open at 0 and 180. So if we went and used a toric periphery, yes, we would fix up what was happening here and here, but we'd actually open it up even further here and here. So this is a most unusual case where the actual corneal toricity does not extend out the same onto the sclera. So in this case, the only way to correct that would be use a toric periphery over the cornea and then use quadrant-specific edge lifts outside the limbus to control the lift outside the limbus. So the majority of you, in fact, got, that's a very difficult fitting, but it does show the importance of looking very carefully what is happening with your foot, both inside the limbus and also outside the limbus. So this is my first case ever that I fitted a toric periphery, and I like to quote it because it taught me a very good lesson. I decided to fit this gentleman. He had worn a XL lens for about 2 years, and he started to get injection at 3 and 9 o'clock because the lens was slightly tight there. So I decided to fit a toric periphery, got the lens made. He came back to me and he said, "Paul, this is the most comfortable lens I've ever worn. I can wear it all day. I'm not getting red eyes anymore. It's great." Well, I looked at it and I thought, well, I can improve this fit a little bit because it's still too open, particularly at 270. So in my wisdom, I decided to use a 1.6 instead of a 1.2, and I fully corrected the amount of toricity. We can still see a little bit of fluorescent entering under the edge, but it has closed the edge down quite a lot. So confident, I said to him, expecting this was going to be even better than the last lens. How did he find this lens? What was his reply? Not as good as the last lens. And it taught me a very, very good lesson, that some misalignment is desirable to get tear exchange with XL. We don't normally talk about tear exchange with semi-scleral lenses. With XL, a little bit of misalignment is absolutely desirable. Here you can see an undercorrected 1.2 toricity, standard toricity on this cornea, and we're still getting a little bubbles. These are probably entering somewhere because of the excess lift, probably inferiorly. Went to 1.8 and immediately we've evened up the pattern. We've got a nice even bearing area and a nice even fluorescent pattern around the edge of the lens. If you see staining with XL onto the cornea, as you can see here, or on the limbus or outside the limbus, then certainly you should consider a toric periphery may be required. Question 3, and this is a little bit more difficult again, but let's see who can get this right. What Rose K2 XL design or parameters would you fit here? And you have 5 different options that you can fit. So the current lens is a 6.6, 14.6, -10. Take good notice of the landing zone. It might give you a clue as to what you have to do here. There you go. I can hand that over to you for the polling here. I can't see the polling coming up yet. So unfortunately, I can't see the polling there. I'll just click up here and see if it does. Ah, yes, we've got it now.
We don't have a poll for this one, Paul.
Okay, so we have, I don't have that polling showing at all. Do you, Majid?
I'm checking with Yara, Dr. Paul.
Thank you. It is.
Sorry, we don't have a poll here, Dr. Paul, so maybe we can continue.
Okay, so we don't have the polling for this particular slide. Is that correct?
Yes.
Okay. So the answer here I will give you, see we don't have the polling, is number 3. The reason why is this. If we look at the current lens, it's a 6.6 -10 standard lift. It's showing a little bit of touch here. It's showing a very wide bearing area here inside the limbus, and we are certainly bearing outside the limbus at 3 and 9 o'clock. So a toric periphery is definitely indicated. So the first option was a 6.6. Remember what I said, if you use a toric periphery, it will flatten the central fit because this bearing here and here will be reduced. The lens will sit back closer to the cornea. So this is not an option. What about a